Oracle racing yacht is going back and forth out here. So at lunch, we're going to be manning up some rowboats, and we're going to go take it. Okay, who's in? All right. No, we shouldn't do that. Probably, we're just going to do this from shore. So our first speaker here, he probably doesn't need much of an introduction, but I'm going to try to do it anyway. It's kind of a personal thing for me. Because of Adrian is why I got involved with Cassandra. And he was the one who told me, hey, you should try this out. So Adrian Cockcroft is the director of cloud architecture at Netflix. You've probably seen a few of his talks. But today, he's coming to you as a Netflix open source guy. He's been doing Cassandra for a really long time. Probably one of the foremost speakers on just how to deploy this and do it right. So thank you very much for being here, and take it away.
Okay, thank you. All right, slides. Hey, I guess I should stand out here. Okay, so I'm going to talk about open source tools and benchmarks. I've got a new benchmark in there. Who was here last year? Who was at the Cassandra Summit last year? I did a live benchmark that year. I'm not doing a live benchmark this year. That was too nerve-wracking for everyone else. But we have done some interesting work since then. So I'm going to talk to you about cloud native. Netflix is a cloud native application, explain how that works. Talk about the global architecture and how that's basically using Cassandra to ship the bits around the world. And then the open source components we use to do that. And we have now over 30 open source projects. There's another one coming out tomorrow, another one next Monday, and a couple more the week after that. So we're pretty much releasing an open source project about once a week right now. And people are getting lost in all these stupid names and acronyms that we have for it. So I'll try and give you a guidebook to how to decode all our components and how they work together. So starting off looking at cloud native. Cloud native is basically an application, a way to build your applications that run in the cloud where we're really optimizing for speed. We're optimizing for time to market because Netflix is making a global land grab. We're trying to build out in a new category area of streaming video, and we're also trying to do that on a global basis. We're trying to, one by one, working through all the countries in the world. So that's a good case for doing something where you have a very elastic need for compute, and it's growing rapidly. It also, time to market wins if you're trying to disrupt your competitors. Hopefully, and you've heard of the OODA loop. That means observe, orient, decide, act. It was a concept that came out of, I think, the Korean War, where aircraft in dogfighting were trying to get inside their competitor's ability to respond. So if you can get inside your competitor's ability to respond, they're looking at what you're doing, they start responding to it. By the time they figure that out, you're already looped around and you're attacking them from behind or something. So that's disrupting competitors, a big piece of going fast. And basically, anything delivered as web services lets you do this. If you're delivering packaged software, it's incredibly hard to do it fast enough. So what do I mean by soon? What I mean is that if I have an idea or somebody at work has an idea for something they want to deliver to a customer, the time to deliver it to the customer base is measured in days rather than months. If we decide we need hardware to run a benchmark or to deploy a new system, it takes minutes to deploy it. You decide I want to do it, you go to the console, you click some buttons, 10 minutes later you have a Cassandra cluster. That was the benchmark I did last year. Don't have to go talk to IT and argue with people and talk to people in finance about budgeting and things and take weeks to build it. And then if anything goes wrong, you want to be able to tell that it went wrong in seconds, and you want to be able to automatically respond in seconds or be able to see what happened. So incident response, if you can do that in seconds, then you can actually do lots of things that are slightly broken, but you spot them really quickly when it matters, and you can fix them really quickly. So I'll talk about how we do that. So this is really tipping the balance. I did a talk recently called Utopia, Dystopia as a Service. So instead of trying to make everything cheaper, we run it fairly inefficiently because we're trying to go faster. We don't try and make stuff better and make our code better. It's slightly broken, but it doesn't matter because we're going faster. And we don't leave everything alone. There isn't a lot of static code, a lot of things sitting there for long enough for us to tune them because everything's dynamic. Everything's growing and shrinking and responding to the market and responding to capacity demands. But this balance of doing everything sooner actually helps us be more competitive. So this gives us a new engineering challenge. We're trying to construct this highly agile and highly available service from ephemeral and often broken components. And our own software is the source of most of the brokenness. And if you do it right, you can go at incredible speed. We can roll things out, and we can be running on a continuous update basis. But the service as a whole keeps working. So there's some inspiration for trying to do this. I've got a few books here. Release It. They made me reformat my slides to 16:9, so a bunch of these things got squished a little bit. So Release It. It's a pretty well-known book at this point by Michael Nygaard. If you're trying to keep stuff running in production, you should go read that. Thinking in systems isn't really about computers. It's more about economics and about large-scale systemic behavior. If you're interested in chaos theory and complexity and how systems behave, it's a very interesting book to go look at. Antifragile came out last year. We use a lot of antifragile patterns. The concept here is that if you keep trying to damage something, eventually it gets stronger. A little bit like working out. You feel really bad the next day, you ache, but the day after that, you're a little bit stronger than you were before you worked out. Drift into Failure is an interesting book. It's a really bad book to be reading if you're getting on a plane soon, or if you're on a plane. Most of his examples consist of planes falling out of the sky and people dying in hospital because systems just gradually build up sort of technical debt in a sort of a failure way, and everything's working fine, and then a plane falls out of the sky. Oh, it's never done that before, But the reason why it fell out of the sky is a series of perfectly reasonable decisions that were made that, in aggregate, over some period of time, turn into something at some point is going to fail. So, very cool book. If you're trying to deal with the human side of operating systems, you need to understand what people see as obvious, things that are obvious in hindsight. If you're doing incident reviews, well, it's obvious why everything died. We're stupid. No, it's not because you're stupid. It's because things are only obvious in hindsight. So understanding how to make things obvious before before it breaks is an important aspect. So this is more a book about sociology and psychology of people. We're doing a lot of REST APIs right now, and we're consuming a lot of REST APIs, and a lot of them are really nasty, a lot of really badly designed ones. And George Rees, if you follow him on Twitter, is sort of continuously ranting about bad APIs, and eventually he wrote a book. It's a short book, definitely worth reading. It's full of all the anti-patterns of things that you shouldn't put in an API. And finally, Cloudnomics. Joe Wyman this is a really, I call it, it's an exhaustive book. It's really quite hard to read to get all the way to the end of it, but he has all of the economics of cloud computing and how to think about the cost model and all of the behavior. So this is much more of a management book about, what is the business value of cloud computing. So that's the inspiration. But genius is 1% inspiration and 99% perspiration. We had a bit of Thomas Edison earlier. That wasn't coordinated. So this is our perspiration. We've been working on NetflixOSS. It's a cloud-native open-source platform for some years. About a year ago, we wrapped this sort of brand around it and started releasing pieces of it. And it's all on GitHub. And it has evolved. We started off 2009 to 10. We were really bleeding edge. We were making things up, figuring things out, trying things 4 different ways, working out which one worked. There were a few guidelines from, say, Google white papers and Amazon white papers, but we didn't have much to follow. 2011, 2012, as we went out and started talking about it, a common pattern emerged. There are other companies working in this way. We shared ideas, and we've evolved something that cloud native has become more of a common pattern now. What we're doing this year and going forwards is sharing that pattern by releasing open source, the pieces that make up that. And it's because we don't regard this as being a competitive advantage for Netflix, having a cloud-native application. Our competitive advantage comes from having exclusive rights to interesting content you want to watch and lots of data about people that we can use for personalization algorithms. So the platform infrastructure is a means to an end that we're interested in sharing with people so that we can make that platform better by having an ecosystem around it. So our goals here, establish our solutions as best practices, as standards, test them in the marketplace of ideas. So we release something, people say that's stupid, but there's a better way of doing it. There's another open source package that does it better. We start cross-learning. We're also trying to hire, retain, and engage top engineers. That's been working out quite well. We have several people that have joined Netflix purely because of our open source program. That works really well as a motivating thing for the people that we have as well. We're building up Netflix as a technology brand. If you go to any presentation on cloud, they have to mention Netflix at least once. I think we had that in the previous keynote, so keeping that going. And also to benefit from the shared ecosystem. So that's why we're doing this. But what we're also looking for is some of your perspiration, right? We've been doing all this work, and we've launched a cloud prize. So this is a prize for contributions that are related to our open source platform. And a lot of those contributions could be around Cassandra, so I'm going to highlight those as I go through. You enter this prize by going to GitHub, looking for the Cloud Prize project and forking it. So it's basically, if you don't know what GitHub is, you shouldn't be entering this prize. That's kind of one of the filters here. We had a couple of confused people trying to give us ideas for making Netflix movies behavior better. This is about the platform. So we have some categories for the way this prize should work. Best example application mashup. We have a couple of those out there already. There's one that Netflix did, and there's one called Flux Capacitor that a guy that used to work at Netflix built. The best new monkey. Monkeys are the automation things. Think of them as like a Unix daemon, but running as a service in the cloud that does some automation. We have Chaos Monkey and things. So you can invent a new monkey. The best contribution to code quality. If there's some QA engineers out there, you can come in, or anyone working with our tools, if you contribute bug reports, we'll just tot up who has the biggest number of bug reports and made the biggest difference. At the end of the day, we'll give them a prize. The best new feature added to an existing project. Best contribution to operational tools. So if you're not maybe a mainstream Java programmer, you want to work on some of the Python-based tooling that we've built, or just running stuff around the edge, integrating monitoring and management tools into our systems, ones that we maybe don't use but other people are interested in using. Portability enhancement. That might mean the Eucalyptus guys are sort of entering this by porting parts of our tools to Eucalyptus. You could port in to a different database, there's a lot of options there. Contribution to performance, performance engineers. If you just do benchmarking on our stuff and point out where it's slow, that counts as an entry. So trying to get kind of a broader view than just having people beating on the code. Best Datastore integration. Probably the wrong audience for this, but I have suggested that why doesn't somebody see if they can get React working with our tools. We got a boo from anybody. Okay, good. One of the other ideas I've got is, well, we have Astanax, which is our client library. You could make that work with Amazon DynamoDB, for example, and just have that as a compatible interface. Those kinds of things, just broadening the choices that we have. Best usability enhancement. We have a bunch of tools that have user interfaces, so you could work on all that. And finally, in case we missed something, we have a Judge's Choice Award for the best overall thing or something that didn't fit into a category. So 10 categories. Each of these categories has a prize. These are the people that are choosing who wins. Many of you probably know about QCon. QCon San Francisco is a great conference. I know as one of the organizers of that. Simon Wardley from England is a strategist on open source. Martin Fowler was one of the Agile Manifesto signatories. Werner Vogels, who's kicked in some additional prizes I'll talk about in a minute. Joe Weinman, who I mentioned his book a little earlier, and my manager. And if we get a tie, my manager will sort of step back and see who of the other 5 picks who won. So these are the 6 people you're trying to impress. So what do you win? You've got 10 categories. You're going to get to go to reInvent in Las Vegas in November. There's a trophy. It's a cool trophy. I don't have a picture of it yet. We're still working on that. It'll be more than just a boring trophy. It'll be a very cool trophy. $10,000 cash and 5,000 in Amazon credits coming from AWS. So AWS credits. So that's the prize. We got 10 of those prizes, and including the trip to Vegas and everything. There's roughly sort of 20K worth of value there. So that's what we've got. We're trying to encourage people to add a bit of perspiration to what we've done, and leverage it further. So just trying to get attention, get your attention span to come and do something. And if you're working and using any of our software, just go and put a prize entry up and list what you've been doing. We're just interested to know, keep track of everything. So this is a little summary of that. We opened registration. There's a 6-month period. We started this in March. It runs till September. So I know everyone procrastinates and waits till the last weekend before they write any code, but there's some you get extra credits if you do something by July 17th, because we're having another open source meetup at Netflix where we're going to feature contributions. Okay. So let's look at Netflix streaming and how that operates. This is a cloud-native application based on this open source platform. So most of you probably have Netflix. This is roughly what it looks like. You see a bunch of movies picked for me and some friends' favorites because I'm hooked up with the Facebook integration. And this is how it works in the background. We have a customer device in blue. Everything in yellow, or the yellowy orange color here, is running on AWS. And the red box is our CDN. So you talk to the website or Discover API, find out about everything. You've got user data coming from Cassandra, personalization data coming from Cassandra. Then we have the streaming API after you've hit play. We get the DRM data. We do quality of service logging, which gets written into Cassandra. It remembers where you are in all your different movies for bookmarks. Again, Cassandra again. And then behind OpenConnect, the CDN boxes, the health of all of our CDN boxes is also managed in a backend that does CDN management and steering and content encoding. Oh, sorry, and that's done with Cassandra. Content encoding is basically ingesting all of the movies from the studios and crunching through them. And that might be running Cassandra as well. I'm not quite sure at this point. It keeps changing. So that's how it works at the higher level. So how much bandwidth are we actually doing? This is some data from last November. And you can see Netflix. People occasionally throw around this thing. Netflix is 1/3 of the internet. So this is what's really happening. Peak period applications, fixed access North America. So this is the peak sort of Sunday night, the DSL lines and cable modems across North America, right? Not mobile, not the rest of the world. They're a little bit different. But this is the US. And Netflix is 1/3 of the traffic. And they did an update. And in this update, they mentioned that the total bandwidth went up almost 40% in 6 months. So that's the top line number went up. And we were still roughly 1/3 of that traffic. So one of the things people keep mentioning is, well, what are your competitors doing? Well, there's a competitor. We're 18 times the bandwidth of Amazon Prime, and 6 months later, we're 25 times the bandwidth of Amazon Prime. I had to actually look it up. They weren't even in the top 10. So not too concerned about that as a major, we're concerned about them as a competitor, but in terms of traction, I like the way these numbers are moving right now. But there's a good reason why everyone has Amazon Prime. Anyway, I have Amazon Prime. I don't watch anything. It's with shipping, right? Okay, so going back to what Netflix looks like, this is the flow of traffic behind our home page. The Start Here button, where is it? This thing here. That is a few hundred web servers, all Tomcat servers. Out here you've got, it's all Java end-to-end. Using App Dynamics, we track all these. So there's a Cassandra cluster. There's a Memcache. There's a bunch of things. So this is from a little while ago, but this shows you the complexity of what we call a microservice architecture. And by microservice, we mean each server does one thing. There's a single function service. It's not so much that it's small. Most of these things have sort of 20 gigabyte heaps, Java apps. But that's basically what's going on. They're pretty big. But they are, they're single function, and you replicate them, and what's the right way of thinking about this? The scope of a service is very narrow, so the failure boundary is very narrow, so it's very identifiable when anything breaks. So if that service breaks, the site keeps working. Maybe you get one of the rows on the home page no longer appears and is filled in with some other row. So that's the way we work. By having single functions, it's very easy to identify what went wrong. In the old days, we used to have lots of jar files that would be integrated every few weeks into this massive blob of code, and when it broke, nobody could figure out which jar file was responsible. Now that you've got a REST call, and this service will go red, and App Dynamics and other tooling will tell you this thing's reporting the errors. This is a simplified view of all of the services talking to all of them. So this is not just the home page, this is sort of everything. In fact, this is a very simplified version. The real version is, we call it the Death Star. You can't actually render it anymore. But this one was one. I wanted a picture that just showed that some complexity. And we test this by killing individual services using Chaos Monkey and using Latency Monkey to inject errors into it. So this is part of the sort of resilience anti-fragile testing. But what we actually do is we run 3 copies. So that's the same diagram replicated 3 times. So we have 3 availability zones, 3 buildings or data centers. At the bottom, we have Cassandra and EVCache, which is our memcached wrapper. And the load balancers spread traffic over all of them. And once you land in one of these zones, mostly you're calling services within that zone. We have zone-aware routing, so you don't keep calling the machines in the other zone. It's a little more slower, it's a little more, it'll cost a little bit more, but it also creates more failure opportunities because you don't want to be if you lose a zone, you don't want to be timing out on waiting to talk to it. So all of the state you're writing is written into the bottom into Cassandra, and that cross-replicates automatically the way Cassandra does with RF equals 3. And EVCache, where we explicitly do 3 writes, and if any of them fail, it's memcache. It doesn't really matter. It's just there for caching. So we don't attempt to be consistent with memcache. EVCache is a library that basically wraps memcached to do this sort of replication that we need here. So we test this with Chaos Gorilla. We do this every quarter. We kill 1/3 of our infrastructure in production just to see if it survives. And we did this a few months ago and we found a few bugs, but it didn't take the site down. Basically, the response to losing a zone is to turn the load balancer off so we're no longer sending traffic to it. And everything keeps running on 2 out of 3. Because we're using quorum, 2 out of 3 works, everything keeps working. So this has happened multiple times, and this is the basic Chaos Gorilla test that we run every quarter to prove that we can still do this. If you're maintaining Cassandra because you're updating an individual instance, the replica of part of the data in one zone will disappear. So those machines in that zone won't be able to pick up the copy of data that's in that zone, which they preferentially talk to because of the lower latency to talk to within zone. So the replication stops working because that one Cassandra node is being updated to a new version of Cassandra or something. And so basically, in that case, all of the instances in that one zone will talk across zone to pick up copies of the data. So that's basically what happens whenever an individual Cassandra node drops out of gossip and is unavailable. So that works fine. One of the things we've been doing for a little while now is running in Europe using a global Cassandra. So we have, in Europe, load balancers, and in the US East, load balancers spreading the traffic in. And at the back end, Cassandra is connecting us to give us our global service. If anything goes wrong with the connection between the two, everything keeps working. This is the key thing. We can lose all of the US, or all of the Europe, and everything, the other continent keeps working. So this is really important. This has worked very well in production for now like a year and a half. So these are the things that can go wrong and what to do about it. Application failure. We're pushing new code all the time. We expect a fairly large proportion of those failures to be broken. We have automatic degraded response, and we wrap everything around with circuit breakers and bulkheads, and we can handle things being broken, but we also try and detect it within seconds and respond within seconds if possible. So it means that it's a very there's a bias to action, basically, in getting new code out. You don't have to put it through QA for weeks. You can just say, well, most of the time it works. We'll try it. Oops, we figure that and back out. So it's a little bit sort of taking a bit of a liberty, but it does work. Region failure we've had a few times in the last year. It doesn't happen that often. What we want to get to is be able to switch traffic between regions, and I'll talk about that next. We're working on that. Zone failure is something that we expect to happen reasonably often and to be able to deal with automatically and transparently so the customers don't see it. We've had data center failures that have taken our services out. We have things like hardware security modules in our data center, and we've migrated those to the cloud now. So you saw AWS come out with HSM recently, largely because we beat them up to go and do it, because we wanted it. When they talked to other people, turns out everyone else wanted it as well. So that's one of the ways that we cut our data center dependencies, and that's helped us be more available. Data store failure, by that I mean we either wrote data, we scribbled data into Cassandra, or Cassandra itself corrupted the data. We do continuous archiving into S3. So if anything goes wrong there, we can restore to some point in time to get back to a working data store. And if S3 breaks, we actually have another copy of that data in another Amazon account in another region. We do a daily sort of copy of S3 to S3 from a remote archive. So we're pretty well covered for most of the failure modes that we could run into. So let's look a bit to how we actually do highly available storage. So this is based largely on Cassandra. And this is sort of generically what one of our services looks like. This is another app dynamics diagram showing lots and lots of REST clients. The thing in the middle isn't Cassandra. This is our REST data access layer. So it's a REST service that abstracts whatever this data store is into a single function, a single data store. So we have over 50 Cassandra clusters, over 50 different data stores. So this is denormalized to the point where every table or every materialized view or whatever you'd normally have in a regular sort of relational database is in a separate cluster managed by a separate team with its own update rate, its own capacity problems, its own whatever we're doing, right? So that means that you can't do join because you're not talking to one cluster anymore. You have to do all of your joining in the application layer. And it's much more like, say, integrating a Twitter API, a Google API, and a Facebook API into your application. These are abstracted REST applications from each of the teams within Netflix exports its services as a REST application. We have over 1,000 nodes of Cassandra running. I'd say since, I'm not sure, we're maybe 400 or 500 of them now, probably SSD. We've been converting them gradually over the last year. There's over 30 terabytes of backup, compressed backup, that gets stored in S3 every day. And we do over 1 million writes per second to some of our clusters. Having this middle data tier lets you do a few clever things. One is that you can tee data off into an old data store, the data center. So I wrote it at the bottom, this optional data center here. The way you transition out of a data center relational model is you build a data access layer between your app and the data center SQL table or whatever, and then you gradually tee that off into Cassandra, and then you move all of your applications to use your data access layer, and then eventually you turn off the access to the old data store. So there's kind of a gradual migration, but you do it by hiding behind this stateless data access service, and we've done that for all of our different data sources. Okay, let's see. More to say on that. So each of those icons on this show is over 3 zones and potentially hundreds of actual individual servers. All right. So each of those stateless microservices look like this. There's a base AMI. We're currently in the transition from CentOS to Ubuntu. There's a copy of Java with Tomcat that consumes most of the memory on it. That's running your application and a bunch of standard packages and things that we have a health check, we have status, JMX, all that kind of stuff. So this is our stateless service architecture. Most of our services are running this way. The way that Cassandra looks is a little different. If you take that wrapped up Tomcat server that was the main box here, the big bluish box, and we put that over in the top left corner, that's now Tomcat running our Preem code, which is one of our open. How many people here use Priam? I got a few? Yeah, I got a few hands up. Okay. So this is all of the helper software we needed to manage Cassandra in production. And we want, instead of putting it all in Cassandra itself, we put it on the side. And it's really, if you're running Cassandra on AWS, Priam is just automation to make that easy. That's how I can create a Cassandra cluster in 10 minutes by just deploying a bunch of machines, and they self-organize using Priam into a Cassandra cluster. The main JDK is running Cassandra with something like a 6 to 8 gigabyte heap, and then we use the rest of memory for either the Cassandra off-heap storage or file system space. Key thing here is we use the local ephemeral disk space. There's no mirroring within this machine. The mirroring is between Cassandra instances across zones. So everything we write is written to 3 zones. There's 3 copies of it. And then eventually it finds its way onto the 2 terabytes of SSD or 1.6 terabytes of local hard drive on the instance types we use. Okay, commit, log, and SS tables all written in there. Just want to make sure people understand we're not using attached storage. We're using the local ephemeral storage, and that's been working very well for us. That way, when you talk to the SSD, there's no network getting in the way. You can get a gigabyte per second for SSD at around 1/10 of a millisecond, random access. You can do 100,000 IOPS of read or write traffic. And that, at that point, all your oh dear, I'm doing a compaction problem sort of go away. It's a very nice system. So this is what Priam does. We've been building this for a little while. It's one of the early projects we open sourced. Zero-touch auto configuration, it automatically replaces broken instances. So if we lose an instance for some reason, the autoscaler will recreate it. And when it comes up, Priam will figure out that it's replacing a node in an existing cluster and automatically bootstrap itself with the data and do repairs to get itself back into state. So completely hands-off. If we lose any nodes in the cluster, takes however long it takes to read the data, to bootstrap. So tens of minutes, basically. We do the full incremental backup and restore. You can hit Priam with a URL which will basically cause it to restore to a point in time. You can also use it to grow and shrink the Cassandra ring. So there's a ring doubling. It will do the token layout for managing doubling the size of the ring. And that was the demo I did last year. If you pull up last year Cassandra Summit presentation, I fired up a SSD and a non-SSD 12-node cluster live on stage from nothing, doubled the size of it, ran some benchmark load, doubled the size of both those clusters, and then shut them down and did all that within a 1-hour talk. So what are we doing now? Jason Brown's somewhere around here. He's the committer that we have working on Cassandra. And he's been working on updating Priam for 1.2 and for Vnodes. There's some work's been done here for restructuring it, but we have to think about a lot harder about how we're doing backups. The way we do backups right now is that each Cassandra node has one token, so we do all the backups relative to that token. With Vnodes, it's a little more complex. So this is an opportunity to make a cloud prize entry. If anyone wants to work on this or work with us on this, we're going to have to figure this out ourselves at some point. But this is basically going to block us from using Vnodes until we figure out how to back up Cassandra in a new way, because our current mode is based on storing the data for one token in S3 as a file. So I'm going to put that logo up a bunch of times. So anyone working in this area, talk to us, put a cloud prize entry in, and we'll work together, and hopefully you'll win something. Okay, so we do big data, because this is the big data place, right? So when I think about big data, and I think about trying to do it in a data center, I think that must be incredibly frustrating, because you have a fixed size cluster and everyone's trying to fit their analytics jobs into that cluster. We turned it inside out. We create clusters that are the right size for answering whatever question we have right now. And we never have to wait for space and never have to wait for answers, because we can scale dynamically and elastically, have any size big data analytics we want to run against our data source. And this is what it looks like. Any of you going to the Hadoop Summit in a week or two, there'll be a lot more on this, and we're open sourcing this entire framework will be open sourced before the Hadoop Summit, as well as a pig visualization tool called Lipstick, right? Because you've got to have lipstick on your pigs. So what we've got here is data coming in from cloud services. We've got event data, about 100 billion events a day flowing in. And then we have, from Cassandra, we're pulling in dimension data. That's like the universe of customer IDs. That's what I mean by dimension data. We bring that in, and we actually put it in S3. So S3 is our data warehouse. It just keeps growing. It's elastic. You don't have to worry about, I need another 4 terabytes of S3. I don't have to provision disks to do that. At the bottom, we have a few Cassandra clusters. We have a 1,300 node cluster that does just continuously processing all of the regular stuff we do to clean data up. We have an 800 node cluster that's used as the analytics cluster for most analytic jobs. The one takes the sort of base workload of people loading up data. And if you want to do anything special, you just start another cluster. And because our data is in S3, all of these clusters have access to the same data. They can all read from S3 and write back to S3. If you put data inside Hadoop, it's all sitting in HDFS, and then you have to send your analytics to that cluster to get at that data. So by putting the data in S3, we're able to do lots of analytics in parallel. We can do upgrades to Hadoop versions by having clusters side by side, things like that. Now, every night we auto-scale our machines down, so we have fewer API servers running, and we have leftover reservations, machines we reserved that we're not using. And we fire up a few clusters, 150 node clusters for doing the daily sort of ETL rollup. You know, there's all that daily business intelligence stuff, what happened yesterday. So past midnight, we have spare machines, so we effectively have some free clusters that we create just to process through that. So this entire system for managing this is called Genie, and we have that coming up soon. We did a blog post on it in January, and we're open sourcing it before the summit. So I mentioned on here, it says adjust this. This is the tool we did for that. Our data is spread across up to 50 clusters. We need to renormalize it. We're trying to, at some point you have to do that join in order to do the business intelligence work. So what we built was a Hadoop cluster that has an input formatter that knows how to read SS tables, Cassandra backup tables. Aegisthus is the person that killed Cassandra in Greek mythology. So this works on a dead Cassandra cluster. All you need is the backups. That's why we called it Aegisthus. Well, the team that they were able to kill having a running cluster by doing it this way. And then we put it in the Teradata. We put it in S3. We still have a little Teradata running on the side, but it's gradually being replaced by a combination of Hadoop and Amazon Redshift. Okay, so let's look at the global architecture and some benchmarks. If you think about what happens with a global Cassandra cluster, there's local client traffic coming in from the top, logically. There's synchronous replication going to the other replicas in that zone, within zones within a region, and we have asynchronous replication going cross regions. So to manage that, we built our own client library. Who uses Astanax here? Hands? Okay, more people, I thought so. That's one of our most popular projects. We ran into problems with Hector, as many other people did, which was the other previous Java client. And Astanax was sort of a rewrite of Hector. It's the son of Hector in mythology. So a few things here. One is it abstracts the connection pool from the protocol. So it lets us manage retries and failure modes much more cleanly. It's got a fluent API that's quite convenient for using. We don't do all that string chopping and slicing that you typically do with SQL or CQL queries. It's token aware, and I'll mention that in a minute, what I mean by that. There's a new feature that's been put in recently or is in development right now, which is a batch manager, so that you can queue up a series of requests and execute them as a batch. And there are lots of useful recipes. The thing that Iran is currently working on is an entity mapper using JPA annotations. And Iran's not here today, but he'll be here tomorrow. And hopefully anybody that's really into Astanax can find him and talk to it. So Iran Landau. Here's some of the recipes, and one of the things that we'd be looking for as cloud prize entries is more recipes. So there's a distributed row lock that doesn't need Zookeeper, or there's a version that you can use Zookeeper integration if you want to as well. Multi-region row lock, uniqueness constraint, a multi-row uniqueness constraint. Large file storage. You want to store a gigabyte-sized object into Cassandra, you soon find it's a really bad idea because it blows everything up when you try and read and write it. What this does is it chunks it up into 256K, which is a good chunk size, and then multi-threads the reads and writes. If you're used to S3, which has multi-part writes, it's basically the same thing. So the point about these recipes is this is all the stuff that our developers over the time have stumbled into, built a bad version of, we've debugged it, figured it out, worked out how to make it work right, and then published it as a recipe so that the next developer just picks up the recipe and uses it. So this is probably the main value of Astanax at this point. These are really high-level, well-debugged recipes. Jonathan talked a little bit earlier about durable message queue and the ways not to do it. This is an implementation of the right way to do a durable message queue with the proper range query so that you don't do millions of, you don't run into the problem of having lots of tombstones in your query. So it's code that implements this correctly so you don't have to think about it. I mean, we use SQS as a message queue for most of our systems, but it has a timeout so the data doesn't last forever. This is a message queue where you can leave stuff in it forever if you want to. We've also got one contributed recipe right now, which is a high cardinality reverse index, and that's currently in the review process, not been posted yet, but it's a pull request for it. So it's definitely looking for more recipes. Anyone using Astanax, if you've implemented something that looks a bit like a pattern, throw it in there. So futures, we've been talking about what's happening next, and particularly with the new driver. Our commitment here is to maintain back compatibility. We have a big code base sitting on top of Astanax. These recipes are very powerful. All of that's going to stay there. We're not going to walk away from Astanax. We're not going to walk away from these recipes. What we are working on and what we might want contributions for, or contributions with, is we're going to basically take the Java driver that DataStax have published, the Netty 1.2 driver, and build a wrapper over that maintains Astanax API. So it'll be seamless forward compatibility. That's the goal. We're working on it, and we're looking for contributions if people want to help us work on it. There's basic CQL support in current Astanax. We're working on some things that will give better access to the CQL level queries, so you can mix the Astanax fluent model of just talking in basically binary, real objects, and you can also mix in there some of the CQL more text-based queries, select queries. And then we're looking for some Cloud Prize ideas. One of the thoughts I have is that it's kind of a pain to run a really small Cassandra cluster. It's actually somewhat easier to just fire up a really small DynamoDB, but if you run a big DynamoDB cluster, it gets expensive really quickly because they charge you per request. So there's a cutover point where you might have people starting off on Dynamo and then outgrowing it and wanting to move to Cassandra. So what I'd like to see is somebody figure out how to take the Astanax client API and put a DynamoDB backend in behind it so that people can use Astanax and just migrate back and forth between Dynamo and Cassandra. And then just more recipes. Let's see what time I got left. Okay. So explain what I mean by token aware and why Astanax is a little bit cleverer. Hector isn't token aware. A lot of the clients aren't token aware. They just they pick a Cassandra instance at random and say, here's some data, or I want to read something. And the node that they connect to doesn't have that data. So Astanax is aware of the tokens in the cluster. And this, again, needs to be rethought for Vnodes, but this is the way we're currently working. It goes in there, and it says, I know that this is one of the 3 nodes that has a replica, so I'm going to go straight to it. That gives us 1 network hop instead of 2. So that halves the latency, halves the possibility of things going wrong. You get to that node, and that node then farms out the other 2 replicas for you as a coordinator. Now, when you're doing that in multi-region, there's an additional single copy that coordinator then sends across to the other region where it's duplicated, and this is the basic mechanism we have for multi-region replication. So there's an asynchronous replica. It's sort of 100+ milliseconds to go to Europe and about 80 milliseconds to get from east to west in the US. So that's our asynchronous replication mechanism. And this has been working very reliably for us. So I did some benchmarks, and a couple of years ago, this is one I posted, and this slide it turns up in all the DataStax presentations, and I kept seeing these pop-up adverts everywhere for a while, which turns out if you keep clicking through it, you end up at my blog post. The point here wasn't that we were doing 1 million necessarily, it was that it was linear, and we just increased the load, doubled the number of machines, and everything just scaled up. The load on each individual node in the cluster stayed roughly constant as we just kept making it bigger and bigger. And I figured at the time we were just in the 20 to 40 machine kind of level. 288 was way beyond that, so I just sort of stopped at that point. So that was 2011. 2012, we did some benchmarks for the SSD launch that AWS did, and we were able to replace a 48-node M2 4XL on spinning Rust disks with Memcache in front of it with a smaller cluster of Cassandra nodes, which were, because they're SSD, they were able to sustain the read and the writes at the same time without having a Memcache in front. So that was last year, and we benchmarked SSDs last year. So this year, we have a new use case. So we've been doing geographic isolation, US to Europe replication, mostly for subscriber data. So if you sign up in the US, you're a member everywhere in the world, and if you happen to be traveling in Europe, your Netflix just works because we recognize you. That's the model. It's read intensive. So the fact that you're in the middle of watching House of Cards in the US is not known about in Europe. We don't replicate that data. What we're looking at now is regional failover redundancy for the US. We want to go from US East to West, and we want it to, if you happen to live in St. Louis and you keep crossing the Mississippi, and we're sort of flipping you from East Coast to West Coast, because that's roughly where the population splits. What we want is the updates to your bookmarks to appear in both places, those kinds of things. We want, the fact that you like a certain genre to appear in both places. So what that means is we have write-intensive data that we're going to have to replicate both sides, and we've been testing that. So one of the ways we wanted to test it was, well, let's fire it up. So we took one of our biggest clusters, 16 SSD nodes per zone, so that's a 48-node cluster, and that was running in Virginia in US East. And we set up an additional cluster of the same size in Oregon, in US West. And this is it's only recently that Oregon got SSDs, only in the last month or two. And we were able to get 96 SSD nodes. So this is almost 200 terabytes of SSD raw capacity. But the data set we had was, we loaded from S3. It's 18 terabytes of data. We sucked that in from backup. That took a few hours. And that basically, the next thing we did was replicate that data across to Oregon. So we pushed that 18 terabytes to Oregon. I'll show you what happened when we did that in a minute. And then so that caused inter-region traffic, pushing the data over. Then we added test load that roughly matched what we currently do, and then sort of a multiple of that. We were looking for something like three times the traffic level that we currently do on this data set, but making sure that would work regionally. We want to be able to sort of get through the Christmas peak with more capacity. Turns out that we had way more capacity than we needed doing that. So this generates inter-zone traffic, because anything I write into one region is now being replicated within region and across and inter-region. And then just to prove that this worked, we set up a validation load where we wrote as fast as we could 1 million writes with CL1, so that's not fully, the minimum consistency. We wrote them to one region, and then we read back those 1 million writes from the other region and got no data loss and measured the latency and made sure that everything worked. So this was kind of the validation we did to basically prove to ourselves that we could replicate write-intensive data stores from east to west. So I have some diagrams that show what happened when we did this. And outside, there's a booth for Boundary. We use the Boundary tool to monitor this at the network level. So what Boundary does is it's monitoring the network flows. So it can see separately the flow that's going to clients, the flow that's going cross region, and the flow that's going cross zone. And we aggregated all our 96 nodes into one set of flows that we're monitoring here. So this shows us what happened when we were copying the 18 terabytes of data. So it ran at 9.3 gigabits per second into region. So this is basically the data being sent. Some of the nodes had more data than others. So some of them finished here, and then there were a few more that finished. So you can see the overall shape here. We didn't have an evenly balanced cluster in terms of the load on each of them. There was more data on some than others. So went through, copied the data over. I was a little disappointed. This system has 480 gigabits of bisectional bandwidth, and I really thought we'd break the internet with this one, but it only ran at 9 gigabits, so yeah, that's reasonable. But some people thought we wouldn't even be able to do that, so that worked pretty well. I think what happens here is that the bootstrap operation is single-threaded, so we effectively had 48 threads of traffic going across. With SSDs at either end, it really wasn't disk-bound. So next thing is the load where we were basically saying this is how much traffic we need. It turns out that meant 300 or 400, 340 megabytes per second of continuous traffic going back and forth. There's another measure here, which is that Boundary measures the latency, the TCP round-trip latency, and that was 83 milliseconds. So what we have now is, in order to sustain this is, I think, a 5x current traffic level, we're sustaining a few hundred megabits of traffic at 83 milliseconds. While running this, we killed nodes, we broke it, we ran repairs, we did all the things that we'd have to do to maintain it, and everything actually kept working. So this is kind of Cassandra being a little bit indestructible again. Tried to break it, and it worked. So that's kind of nice. And then it's like, well, you have to ramp it up until it breaks. So we just kept going, and we ended up at, I think, 16 times our current traffic, which had spare CPU, spare IOPS, spare network, but I think we ran out of some buffer in the hinted handoff area or something like that. So we need to do a bit of tuning. But as you can see, we're running almost 2 gigabits of traffic continuously. Again, it was running at 83 milliseconds and didn't seem to have any problems. So well, this was all done. It was a pretty big, expensive system to do, but this is a confidence builder for us that we can actually do write-intensive deploys, and we don't have to invent another mechanism for doing cross-system replication, cross-region replication. But at this point, we'd really driven it a bit beyond what it could do. If we need to, when we get to this level, we'll do more tuning, and we'll add more nodes or something. OK. So this is what it looks like once we've got that. We have our regional load balancers on either side. We have our customer, and our customer needs to connect to them. And we're using DNS to route customers to either place. And DNS has options for geographic routing if you're using Ultra or Dyn. AWS doesn't currently have geographic routing, so we're using those two right now. Those are 3 radically different APIs, and they're fairly clunky, bad APIs in some cases. So we've built an open source toolkit called Denominator, and if you're doing anything to do with DNS management, you should be using Denominator. It was written by Adrian Cole, who wrote JClouds. He's working, talking about engineers we've hired because of our open source. He joined us in December. So he's been building this DNS abstraction layer in Java with lots of features, and we're using that to dynamically switch traffic from one region to another. Now, if anything goes wrong with a zone, we just keep working. If anything goes wrong with a region, we use Denominator to switch all of those endpoints to the other region. If anything goes wrong with a load balancer, we can switch the traffic to the other region. And if anything goes wrong with one of our DNS vendors, we can use Denominator to switch the traffic, switch all of that state to a different DNS vendor. It has an independent view of what the state that's being stored in DNS is. It has its own model, because these APIs are so broken that you can't read back what you wrote to them and things like that. So you have to keep something outside that. So this is being wrapped up in a distributed service, again, with Cassandra in the back end, so that even if a region is down, the state that was stored in that region is available globally. So this is a tool we're currently in the middle of rolling out, and Denominate is one of our open source projects you can go play with. Even if you're not using Java, there's a command line version of it that works very nicely. So how does this all fit together? I've got a few minutes to talk about our NetflixOSS platform in total. We got so confused trying to keep track of all the names of these things that we built an example application, which is an RSS reader. And you can see all the different components here. So it's got a front end using this is a base server. There's some logging. This is the service registry for talking to our service. There's our service registry. There's a client for that. Archias is used for configuration property management. And then we use Hystrix for managing communication with bulkheads and circuit breakers. And then we use Servo and Astanax. Servo for sending metrics to AWS, and Astanax for talking to Cassandra. So ties it all together a little bit more. There's an even more sophisticated example application. I think it's at fluxcapacitor.com, but if you look for Chris Fregley happened to own Flux Capacitor domain and decided to just put it up on that. Not sure quite what it does, but something interesting. So if we look at all the different projects we've got, there's basically GitHub full of source code, Maven Central with the binaries in it, and we're working on getting some base AMIs out. This is currently the thing that is really unfortunate. Because we're in this transition from CentOS to Ubuntu, internally we've got a lot of stuff in flight. We're trying to get to Ubuntu so that we can have base AMIs based on the new code rather than re-implementing it on CentOS and then moving on to chain switching out. All that data, I'm sorry, the reformatting didn't work quite well, but we use CloudBees, which is a cloud-based service which runs Jenkins. We use that to run our own bakery. Well, they run the bakery. And that calls Dynaslave. Well, it can use Dynaslave to do build slaves, and they use bake AMIs from the code. So that gives us a set of baked AMIs. We can then use Asgard, which is our console, to deploy those to an Amazon account. We have another tool called Odin, which is an orchestration tool which lets us sequence things in Asgard. So this is our build and deploy system. If you look at the services we have within an Amazon account, we have an Asgard console per account. We have a config service. There's cross-regional Priam backend with Cassandra. There's a dashboard system called Pytheas, which is, some of you maybe have seen the Netflix dashboards. It's the basis for building those. We have a monitoring, the slightly more pastel-looking ones aren't quite out yet. So Atlas for monitoring, we're still working on getting that ready to release. Genie and Lipstick, Hadoop surfaces. And AWS Usage is a cost monitoring tool that we'll be releasing later this month. Within each region, you then want a registry. You want Zookeeper running. We typically have Zookeeper within region, but not cross-region. Edda, which is a history service. Simian Army, all those monkeys running around. And we have a traffic manager, and this one's going to be released later this week, which basically we use for routing and processing the incoming traffic streams as they find their way to applications. And that's those are fairly new announcemements. And then within each zone, you're going to have your own code, Priam, and EV cache, which is sort of per zone, so we lay them out a little differently. Then, to build those applications, there are a whole set of libraries we've produced. So there's Governator for dependency injection, Archias for configuration properties, and Eureka for service registry. So that's the initialization phase of an application. Then, in order to service requests, you need a base server. We have a reactive pattern based on Java, RX Java. Hystrix, which is the circuit breaker library, and Turbine, which gives us 1-second monitoring dashboard so you can see whether your circuit breakers have flipped. Ribbon is the REST client for outbound calls, which also understands zones and zone awareness and routing traffic correctly. Then for accessing data, we have Astanax, obviously. EV cache for memcached. Curator is a Zookeeper pattern library. Zookeeper has recently decided they like this enough that they're sponsoring it as an Apache incubator project. So Curator is the first piece of NetflixOSS, which is now moving up to Apache incubator, and it will eventually, I think, become part of Zookeeper itself. And then Denominator I mentioned for DNS routing. Then there's a bunch of logging I mentioned before. Okay, so I'm running out of time, so there's a bunch of testing and automation. There's a load, anybody using JMeter, we have a Cassandra plugin for dealing with that. Garbage collection visualization, a whole lots of monkeys. So one of the more recent things we did is Explorers. Internally, we have a Cassandra Explorer, Base Server Explorer, and a whole bunch of other things. This is a D3 JavaScript library. It's quite a powerful system just for building libraries. We had this diagram, we showed it last year, a lot of people were interested in it. This is one way we visualize all our Cassandra clusters. Unfortunately, open sourcing it, we cleaned up a bunch of things, and this is currently in the middle of being completely rewritten by Iran, so you have to kind of pigeonhole him over when he's going to have it finished. So this isn't currently out, but it'll be out as an update to the Explorers library. And with these, you mouse over it, you can see all the different clusters and what's going on. This is the Amazon usage tool, reservation-aware cost monitoring, basically. This will be out later this month. So what's coming next is more portability, better availability, making it easier to deploy, contributions from end users, particularly prize winning and prize entries, and contributions from vendors like Eucalyptus, who've already got this ported. There are people working on this for CloudStack and OpenStack as well. And even potentially the Google Cloud people are poking around trying to figure out whether they can run this. So this is where we are. We've got functionality and scale now. We have portability coming, moving from a bunch of loose parts to a whole platform. We're building an ecosystem, sort of a health warning. This is evolving very rapidly. You're jumping on a moving train here. We're iterating very quickly with all this ourselves. And we're trying to make it easier for everyone to become cloud native. So that's the takeaway. And if anyone wants more details, there's a bunch of links here. Well, these slides will be up, but we have lightning talks from our open days that we've had so far earlier this year. There's a security architecture talk. And if you're interested in the cost analysis and optimization, there's a joint talk I did with Jinesh Varia to go look for. Okay, so I'm out of time, I think. Just about on time by my watch anyway. So that's it. Thanks very much. I'll be around through tomorrow afternoon. So see you in the drink up.